All right. So, we're going to go ahead and we're finishing off the semester, and we're going to be talking about op amps. Okay. Now, op amp is just an abbreviation for this really cool part, this really neat component. Op amp is operational amplifier. So, it's an amplifier that's able to perform operations. And that's actually where this name comes from. Comes from the op amp's ability to perform mathematical operations. So, believe it or not, this little part over here, and this would be the schematic symbol for an op amp, is capable of performing all sorts of useful mathematical operations. You could add voltages. So I could take two voltages and add them together. I could have 1 volt on one wire, 2 volts on another wire, and out of this op amp is going to come 3 volts. Um, or you could subtract the two voltages. You could take 3 volts minus 1 volt and end up with 2 volts on the output. You can do multiplication, you can do division, you can even do things like integration and differentiation. So you can perform calculus, analog calculus, using an op amp. These are really useful devices. I've never designed something without them, and hopefully you'll see why they end up being so useful in a minute. Okay, so I'll just start off with this schematic symbol that we have here. Amplifier in general, we always use a triangle to represent it. And in this case, this op amp actually has two inputs. All op amps have two inputs. We denote it with a positive on one and a minus on the other. So just looking at these inputs over here, we have a non-inverting input, which is labeled with the positive sign, and we have an inverting input that's labeled with the negative sign. We also need to power this device. Just like our common emitter amplifiers, our transistor circuits, they need a source of power for them to do anything at all. So we are going to be putting signals into this device as well as getting a signal out of the device, but we need to supply power. So that's why we have V plus, V minus. We actually call these rails. This is the positive rail, and down here is the negative rail. Okay. Now, I don't want to get too caught up in powering these things right away because there's just so much to talk about. Um, so don't worry too much about the power just yet. Um, we have these two inputs and one output. Now, just as a practical frame of reference, when you purchase one of these devices, it's going to look something like this. Now, they come in all sorts of packages. But the basic package that you kind of work with on breadboards is this nice kind of old school DIP package. And DIP just stands for dual inline package. It's that computer chip, that quintessential looking computer chip, kind of looks like a roach. And the part number is always across the top. Now, this package, keep in mind, I can get this package and I can have all sorts of different things inside. I can have a DIP8 package that has a linear regulator inside, or a timer, or any sort of different component. But typically, when you use an op amp in your breadboarding, you're probably going to go to this kind of standard DIP8 package. And then the part number is written across the top. So inside, this is kind of your go-to what everyone teaches when they're talking about op amps, your 741, or specifically your LM741. LM actually is owned by National Semiconductors, the company. Now, inside of this chip, here we go. We have a pin out diagram over here. When you look at the top of it, you're always given your kind of starting point, your reference for pin 1, and we just go around in this counterclockwise or anti-clockwise fashion. Pins 1, 2, 3, 4, 5, 6, 7, 8. And you notice inside we have an op amp over here. We have a non-inverting input, we have an inverting input. Those respectively go to pins 3 and 2, as I've labeled over here. We have the output that is tied to pin 6, and again we have to power this device, so we have the positive rail over here, V+, or you'll also see it referred to as VCC. And you have your negative rail, which is referred to as V- or VEE. That's our negative rail. Pins 1, 8, and 5 are actually not connected to anything in this part. So if I go out and purchase an LM741 in a DIP 8 package, this is what I'm getting. And sometimes you'll see this referred to as NC, 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 just referring to no connection in that case. Okay, so kind of just to set that frame of reference. Now, let's go ahead and let's talk about kind of what this guy does. And before we get started, I'm going to break it into two types of configurations. Okay, we have two configurations that an op amp can be used in. Now the first one is going to be the open loop. Configuration. And the second one is going to be the closed loop. Okay, so two different ways we can kind of use this guy. Okay, our open loop configuration has two inputs and one output, just like we talked about, as our op amp sits there. This would be considered open loop. Now, what does closed loop look like? Now, closing the loop just means that we're going to have a connection going from the output back into one of the inputs of our device. I can do that like this. So we still have some signal being fed into one of the inputs, and on the output we still have some wire that's giving our signal or providing us an output of our signal, but somewhere we have a path from the output all the way back into one of our inputs, or all the way back into both inputs. As long as we have some pathway that exists between the output and the input, we have what's considered a closed loop configuration. Now, this would be referred to as having feedback. It means that as the output produces some value, that output is taken into consideration by the device, meaning that as the output changes, it causes the input to change. As the input changes, the op amp does something else to the output. And therefore, we have this endless loop over here, okay? So it's just closing the loop. Now, I should also say it doesn't matter what's in this pathway. I could have a resistor in here, I could have a transistor, I could have a cap, I could have anything in there. And as long as there is some mechanism that allows the output to affect the input, we have a closed loop, as opposed to our open loop. In this case, we have no pathway coming from the output back into the input. Okay, so these are kind of our two fundamental setups that we could have for any op-amp circuit. Okay, now let's talk about that open loop configuration. Okay, now the open loop configuration, when I first started learning this, I looked at it and I'm like, oh wait, that's way easier, right? It's open loop. What is it once we add this closed loop in here? All of a sudden things seem like they get more complicated. I promise you both are actually really easy to understand. But we have to keep it in these two separate domains of open loop versus closed loop. Okay, so let's look at the open loop configuration. Now, as an amplifier, it's going to amplify the input by something. Or because we have two inputs, it's going to amplify the difference between both of our inputs. So this positive and minus actually kind of really makes sense once you start thinking of your input as actually being two wires, two inputs, two different voltages. So by differential input, all we're saying is V plus minus V minus. Don't worry about this front part here right now. Okay? We have our non-inverting input, and we subtract from that our inverting input. And the signs that we use to make reference to the non-inverting input versus the inverting input really makes sense here. Plus whatever voltage is here minus whatever voltage is here. It's exactly what we're saying here. V plus, and maybe let's do this. Let's call this V in plus and V in minus. And then I'll rewrite that over here because it looks like we're adding. And okay, V in plus minus V in minus. Okay, don't get confused. I'm not saying V in plus minus V in minus. I'm saying V in plus is the value over here. So if V in plus was 3 volts, this whole thing right here would get replaced with 3 volts, right? Same thing with V in minus, okay? The operation is just taking the subtraction or the difference between our two inputs, okay? So that's what this front end is doing. It's just taking the difference between these two inputs. Simply this minus this, okay? Now, as it is an amplifier at heart, we have some gain. And for gain, we always reference that with A. Now, because we have no closed loop configuration here, because we have no pathway from V out back into any one of these inputs, I'm going to refer to this gain as open loop gain because it's kind of a special value. It's an intrinsic value to the part. And as we'll find out in a minute, it actually doesn't matter what it is. It's really high. Okay, so this value is on the order of 10,000 or 100,000. It's really high. Sometimes you open up the data sheet for the part, like I'm going to use a 741, so I go ahead and open up the data sheet for it, and it tells me the open loop gain is going to be 100,000. As you'll see, it actually won't matter. What matters is the open loop gain, or the gain, natural gain of this device with no feedback, is just a super large value. Okay, so we're actually going to break this down into a series of rules. Actually, only 2 rules in one special case, and we'll actually be able to understand and analyze any op-amp circuit. Okay, so I'm going to start off with these lists of rules. we're going to have a rule 1, we're going to have a rule 2, and this special case right here, which I actually just talked about, the op-amp gain is really large. The open loop gain, the natural gain of this op-amp is something on the order of 10,000 or 100,000. Okay, so with this really large gain, it kind of seems like it's a bit useless. But we'll see that there is actually one application for this open loop configuration. So let me go ahead and first say 99% of your circuits with op-amps look like this. Turns out this feedback is crucial for all of the op-amp circuits we're going to look at, except for one. Okay, so let's go ahead and attach some voltages to this open loop configuration. Let's see what happens. Okay. And actually, I'm going to draw this. Let's do this. And for right now, I am actually going to attach this to some power, and you'll see why in a second. I'm going to stick 0 volts for our negative rail, and I'm going to stick, let's say, 5 volts for our positive rail. So the device is being powered between 5 volts and 0 volts. And now let's go ahead and put some values over here. I'm gonna put 1.001 volts on our non-inverting input, and on our inverting input, I'm gonna put 1 volt over here. And we're gonna look at V out. Okay, so remember, it's the difference between the two inputs, so plus 1.001 minus 1 volt, so the difference between these two, multiplied by that incredibly large gain, gives us what the output is going to be. I'm just using kind of our basic equation for how this guy works in the open loop configuration. Now, the equation, this is something you might have to memorize at first, but I think it is intuitive when you think that you're taking the non-inverting, subtracting the inverting, so you're taking the difference, multiplying that by the gain. Okay, so V out is going to be equal to our incredibly large gain multiplied by the difference between our inputs. I'm going to use the signs to help me out here. Plus 1.001 minus 1 volt. And that's going to go ahead and tell us what the output should be. So I'm going to run that math. .001 minus 1 gives us 0.001, 1 millivolt. Tiny voltage, right? Because the difference between these two is very small. And I'll multiply that by our incredibly large gain over here. So times 100,000 gives us 100 volts. That's what our output should be. 100 volts. Seems really high. And my device is only being powered by 5 volts and 0 volts. Okay. Now, here's where we need to pay attention to the power. As it turns out, the output, and for that matter, the inputs as well, cannot be outside of this range. Meaning we can't have negative 1 volts, we can't have negative 10 volts. Similarly, we can't have 10 volts, we can't have 100 volts. So what's going to happen to the output? So let's go ahead and also say Vout must remain within positive and negative rails. Okay, so as it turns out here, we have a little contradiction. We're supposed to be outputting 100 volts, but this device is not capable of outputting 100 volts in this current powering setup here, right? It can actually only go as high as 5 volts. So this 100 volts, it's not able to get to 100 volts. It actually gets to 5 volts, our highest positive rail, okay? So when we put in 1.001 volts and 1 volt on our inputs, we actually get 5 volts. Now, let me go ahead and do this same exact circuit, and all I'm going to do is swap this 1 volt and 1.001 volts. Okay, so I'll go ahead and redraw this. Keep everything the same, except I'm going to flip and put 1 volt here and 1.001 volts on our inverting input. Now let's go ahead and calculate what Vout ends up being equal to. So same thing, Vout is going to be equal to our incredibly large open loop gain times the difference between our two inputs, so plus 1 minus 1.001. Now notice we're getting minus 0.001 or minus 1 millivolt times 100,000. So we should get minus 100. But wait a second. Remember, I said the output has to stay within the positive and negative rails. Minus 100 volts is clearly well below 0 volts. So that means our minus 100 volts is actually 0 volts. It's as low as it can go, or it's as high as it can go. And notice the difference between these inputs was quite small. So think about what we've just created here. No matter what the difference is, it gets amplified by such an incredibly large value that it maxes or mins to whatever our positive and minus rail is. So think about what function is being performed between these two voltages. Think about that for a second. All right, time's up. We just made a comparator, okay? So this is comparing both of these voltages, and it'll tell us which one is larger. If we get 5 volts, it means our non-inverting input was larger. And if we get 0 volts on the output, it means our inverting input was larger. Okay? So this op amp in its open loop configuration, and this is actually the only useful circuit, well, only, I shouldn't say only, this is the most basic useful circuit that you can make in the open loop configuration, and I don't know what the other open loop configuration circuits might look like. But in the open loop configuration, your op amp is comparing these two inputs. Okay? So, regardless of what the difference is, whichever one's greater is going to cause the output to saturate to either the positive rail or the negative rail. So I'll go ahead and do one more of these. Let's change some things up here. I'm going to go ahead and now power it off of plus 10 volts. And I'm going to do minus 10 volts. And instead of having a small difference, I'll go ahead and do a large difference. Let's do 2 volts here. And let's do 5 volts there. Okay, and now the question would be, what is V out? Okay, perfect question that I would ask. All right, well, V out is going to be equal to our incredibly large gain, our incredibly large open loop gain, 100,000 times plus 2 volts minus 5 volts, so the difference between the two. Well, that's going to be minus 3 volts times 100,000. Minus 300,000 volts. Yeah, right. You're never getting minus 300,000 volts out of this guy. But what you will get is minus 10 volts. Okay, so again, same thing. If our minus is larger than the positive, we get the lowest possible voltage out of this guy, which is minus 10. That's V out. And if the non-inverting input is greater than the inverting input, we get the highest positive voltage out, which would be positive 10. Okay? So that's the open loop configuration. Now, as you can see right now, this isn't a useful amplifier. I'm not really amplifying anything. I mean, kind of. By an incredibly large, unwieldy value that some data sheets won't even tell you because it's so large. We need to do something to tame this amplification, this incredibly large value. So, we're going to need to now start talking about our rules. Okay. Rules. Number 1. This one is always applicable. Even in our previous circuit, this rule always applies. This is true for all op amps. No current flows in or out of the inputs. Okay, no current flows in or out of the inputs. 0 amps in or out of our inputs. That means over here, this wire right here is 0 amps all day long. It's only looking at the voltage. can think of this as really high impedance. Same thing with our other input. 0 amps in or out. I'll go ahead and say high Z inputs. Remember, high impedance means it's a really large resistance tied to ground. 10 megaohms, 100 megaohms. A really high resistance draws little to no current. We're saying it's 0 amps. Okay? And if you remember from our previous amplifier lectures, that's a good thing. We would like to have high impedance, or sufficiently high enough that we can consider the current flowing in or out of the inputs, we can consider those to be negligible. Okay? We get that in this device. As a freebie given. Okay, now this second rule. Applies only in a closed loop configuration. Okay, so this is actually going to only be applicable in a closed loop configuration. Meaning, this rule, whatever I'm about to say, doesn't apply to this circuit because there's no feedback. There's no closed loop over here. The op amp will change its output in order to make the inputs have the same voltage. Okay, the op amp will do whatever it has to in order to keep the inputs at the same voltage. Okay, this rule is what's going to make it super easy for us to analyze almost every op amp circuit that's out there. And so we're going to go ahead and show this rule with what I think is the most important and most often used circuit using an op amp. Okay, this is the most fundamental of our closed loop configuration circuits using an op amp. We have a V in and we have a V out. Now, let's go ahead, put some voltages on here, because given everything we know thus far, we can actually solve this circuit. So I'm going to go ahead and say V in is equal to 1 volt. Now, if you notice, I dropped the power rails. I kind of don't care about them right now. Most of the time when people are talking about op amps, they make the assumption that V out and V in is well within the positive and minus rail. So to keep it simple, don't worry about that positive and minus rail for right now. Don't worry about powering it. But the question we want to know is, what is V out when V in is 1? Well, let's go through our rules and see if anything helps us here. All right, rule number 1, no current flows in or out of the inputs. All right, what does that mean? Well, no current in or out. All right, that's kind of cool. Of both of the inputs. But that didn't really help us to figure out what V out is. All right, maybe rule number 2 is going to help us. Only applicable in a closed loop configuration. Ding, it's a closed loop configuration. I got a pathway from the output back into one of my inputs. All right, so rule number 2 is applicable here. The op-amp will change its input in order to make the the op-amp will change its output in order to make the inputs have the same voltage. All right, another way of saying that, the op-amp will do whatever the hell it has to in order to make both of these voltages equal to each other. So by that rule, if this is 1 volt, what do you think this has to be? Well, if this is 1 volt, I can tell you that this is also 1 volt. We have 1 volt on this wire. We have this 1 volt on the wire. Why? Because the output made it 1 volt. The op-amp from the input side couldn't do anything to this wire, right? It's got 0 amps flowing in or out of this input. So this op-amp isn't going to be able to change anything from this input. But it can absolutely make it 1 volt by making V out equal to 1 volt. See my logic on that one? If this is 1 volt, then the op-amp must have made this 1 volt. How did the op-amp make this 1 volt? By making the output to be 1 volt. So we can always work our way backwards to V out from whatever inputs that we have. All right, so if I put 1 volt here, I get 1 volt out. All right, what about if I changed that? What if instead of What if instead of 1 volt, I made this equal to 3 volts? Well, again, if this is 3 volts, this must be 3 volts. The op-amp will do whatever it has to make both inputs equal to each other. So if this is 3 volts, this must be 3 volts. And how did this become 3 volts? It didn't happen because the input decided to change. It can't do that. It has no ability to source or sink current over here. So the only possible way that this was made to be 3 volts had to be because V out was made to 3 volts. Okay, so now I got 2 examples of this circuit. If I made this 5 volts, this would be 5 volts. If I made this 6 volts, this would be 6 volts. If I made this minus 5 volts, this would be minus 5 volts. Whatever our voltage on the input is what our voltage on the output is going to be. So in general, for this circuit, I can go ahead and say V out equals V in. All right. So that's what this circuit's doing. Let's give it a name. Since the output is following the voltage on the input, let's go ahead and call it the voltage follower. Okay. Since the output is the same as the input and the op-amp seems to be buffering the input from the output, we could also call this an analog buffer. Most people will call it a voltage follower, but analog buffer is totally an acceptable and valid name for it. And some people call it that. Okay, there is one other thing that this is doing. Is this amplifying? Is the output being made to be bigger than the input? It is, by a factor of 1, right? V out equals V in times a gain of 1. Okay, now when you have a gain of 1, we call that unity gain. Okay? So this could also be a non-inverting unity gain amplifier. Okay? Non-inverting. The output is staying the same polarity as our input. If our input's positive, our output is positive. If our input is negative, our output's going to be negative. It is non-inverting. It is not changing the sign of our input. Unity gain, because it's got a gain of 1, and it's an amplifier. So non-inverting unity gain amplifier, okay? Or an analog buffer, or more common in vernacular, voltage follower, okay? Because it's following the voltage. So that's our first circuit. And I don't think that was terribly difficult to understand, as long as we just accept those two rules and run with it. Okay. Let's do something. Well, actually, there was one more thing that I wanted to talk about with this voltage follower. Just remembered. You may ask, why on earth do I even want this circuit? I mean, hell, V out is equal to V in. I can do that. I'll just draw a wire. V in and V out is equal to V in. Yeah, that's true. Yeah, I could just replace this voltage follower with a wire and get the same effect. Except this op-amp does something really useful for us. And if you go back to that common emitter amplifier circuit and you look at how the impedances mess with us, all of a sudden this is now going to make a lot of sense. Why would we use this circuit? Remember, I said earlier, most useful op-amp circuit in the world. Because 0 amps is flowing in or out of this input. This wire doesn't take any current. We call that high Z. And our output, well, our output is not high Z. Our output is actually low Z. If you go back to that lecture, I told you that was going to be so important. Low impedance. Another way of saying it, we have an ability to sink or source a lot of current. High Z, we sink or source little to no current. Okay? So now the buffer thing makes sense. We're buffering the impedances from something here to something over here. So remember that with that common emitter amplifier, between the source and the input to the amplifier, you created this voltage divider situation. Well, this lets us get rid of that problem. We don't have to even calculate the voltage divider, right? Because if I connect something over here, remember I said in the real world, you're always going to have a difference in impedances between the source. You have a ZS, and you have another resistance in here that I'm not drawing, tied to ground, which is also an impedance. And then you'd have to do a voltage divider between these two to find out the true voltage at this pin. Well, once we use an op amp, in most configurations, you don't have to worry about that anymore. All of a sudden, the impedances are negligible because the inputs are considered to be sufficiently high that they have little to no effect on this voltage over here. So you don't have to calculate that. Same thing with the output. We can consider the output to be sufficiently low enough impedance that it doesn't matter. Okay? So that's really kind of the benefit of this voltage divider. And that's why I end up using them so often and in every single design. And every single design I've ever looked at is because it solves that problem. So if I need to hook something up to a microcontroller, let's say I have a microcontroller here, and let's say I have an ADC. Now, that means I can take input from an analog pin. And let's just say that input from an analog pin, let's just create a voltage over here. Let's say our MCU is tied, it's powered off of 5 volts and 0 volts. And let's go ahead and say I have 100 ohms here and I have 100 ohms here. I just created a voltage divider. That gives me a voltage here of 2.5 volts. And let's say I'm going to write a little program that runs on this microcontroller that reads the voltage on this pin and turns it into a digital value. Let's just say it's 8 bits. Well, guess what? This isn't true. It's not 2.5 volts because this analog digital converter has a little resistance over here, an impedance, and this has an output impedance, and this has an input impedance, and I just created a voltage divider between the voltage divider. I have two voltage dividers here, right? I have a voltage divider here, and I have a second one that's created between this and this. So this is no longer 2.5 volts. If I disconnected it, it is. If I didn't have that connected at all, this would be 2.5 volts all day long. But as soon as I make that connection, that turns into something else. I don't know what it is because I don't know the impedance over here, but maybe it's like 2.46 volts, right? It's a little off. Maybe not even enough that you might notice it until something stops working, until something doesn't work anymore. You run into a problem, and you start looking into it, and you realize, oh, wait a second. Yeah, the impedances here are creating a problem. And then you go, well, how am I going to fix that? And you go, well, maybe I can compensate for it in the software. It's kind of a crummy way to do it. Wait a second. Let's use a voltage divider to fix. Let's use a voltage follower to fix that. Okay, so I'm going to take my microcontroller unit with an analog digital converter ADC pin that's converting my analog value into 8 bits. And now I'm going to put the king of all op-amp circuits in here. Positive, minus. There we go. Now this is 2.5 volts. This uses little to no current on our input. The output is whatever our input was. This is now 2.5 volts. This is sufficiently high enough impedance that we don't even have to worry about the input impedance to the ADC anymore. Problem solved. This really will save your bacon. Every single design I've ever made has something like this. Every design you'll look at should have something like this. Yeah, you'll see people online not doing it. They're wrong. Okay, if you're going to properly design something, if you're going to have some sort of medium impedance circuit connected to your microcontroller to an analog digital converter, you should be putting this in there. Okay? So that's where the voltage follower shines. It's for fixing the problems created by bad impedances, right? Golden rule of impedance: always drive a high impedance with a drive a high impedance input with a low impedance output. This is low enough to drive this. This is low enough to, well, I should say, this is high enough that it doesn't matter what we connect here, and this is low enough that it doesn't matter what we connect here. Okay? So that goes ahead and covers this circuit. Now, I do want to go over one more circuit before we're done, because we used our rules, but frankly, it was a little boring, and we never actually did anything useful with it. Well, I shouldn't say that. Created a voltage follower, which is infinitely useful, but we never actually amplified a circuit. So I want to show how we can make signals larger. After all, it's called an op-amp. It's in the name. Okay, now for this next circuit. And I'm not going to actually give the name until we analyze it. And I'm going to have to give some designators for these parts. We're going to call this our F feedback resistor, and this we'll call R1. And over here we'll label this as V in. Over here we'll label this as V out. Okay. Now I could give the equation for V out and just be done with it. But I think it is much more valuable if we figure it out using our two rules. So let's go ahead and let's put some values in here. I'm going to make this equal to 9K. I'm going to make this one equal to 1K. And V in, let's make that equal to 1 volts. Okay, and I'm not going to not worry about power for right now. Okay, what's V out equal to? Can we solve for that using only what we know? Rule number 1, no current in or out of these inputs. This has 0 amps. This has 0 amps. All right. Okay, rule number 1. Didn't really help us there. All right, rule number 2. Do we have feedback? Absolutely. We have a closed loop configuration with feedback. We have some pathway from the output back to one of our inputs. Doesn't matter that we have a bunch of stuff over here. As long as some pathway exists, rule 2 is applicable. And if rule 2 is applicable, and this is equal to 1 volts, what is this equal to? What's the voltage on this inverting pin? Well, it's got to be equal to 1 volt. Okay? So we're going to use that knowledge, work all the way back to V out. Alright, where from here? Well, we have 0 amps on that pin. Okay. This is 1 volt. Well, if this is 1 volt, this is 1 volt, right? This is just connected by a wire. We have 1 volt everywhere across here. Okay, what about over here? We got 0 volts here. Okay, so we have 1 volt over here, 0 volts on the other side of that 1K resistor. Which way is the current flowing through that 1K resistor? Well, current always flows from a high voltage to a low voltage. Alright, what's the value of it? Well, what's the voltage drop across the resistor? Well, if we have 0 volts here and we have 1 volt here, VR1 is equal to 1 volts, right? It has to be. Okay, and if we have a voltage drop of 1 volt across a 1K resistor, what's the current flowing through that 1K resistor? Well, we know the resistance, we know the voltage. Use Ohm's law. All of our old rules will help us. Okay, so I'm going to take 1 volt and I'm going to divide that by 1,000 ohms, and we get 1 milliamp. Alright, cool. We got 1 milliamp flowing down. Where did that 1 milliamp come from? It didn't come from up here because we have 0 amps going through this wire, right? Rule number 1 told us that. So rule number 1 is very useful here. No current. So this 1 milliamp, well, it had to have come from here, right? Ohm's law is still Kirchhoff's current law is still applicable here. We have 0 amps flowing in or out of this wire, and we have 1 milliamp leaving. That means we must have 1 milliamp entering. Okay, so Kirchhoff's current law helped us out there. Okay, now let's figure out what the voltage drop is across this feedback resistor. We know we have 1 milliamp going through it, and we have 9K. So VRF must be equal to 1 milliamp, or V equals IR, so 1 milliamp times 9K equals what? 9 volts. Alright, so we get a 9 volt drop across this feedback resistor. Notice over here, the current is flowing from right to left. That means that this must be higher than this side. Has to be. Current always flows from a higher voltage to a lower voltage. By how much? By 9 volts. So this side must be 9 volts higher than this side. Well, what's this side? This side's at 1 volt. That means over here, we have 10 volts. Okay, so we have 10 volts over here. Well, this is directly connected to V out. V out is equal to 10 volts. So when we put 1 volt in, we get 10 volts out. Alright, do we know what this circuit is doing? It looks like it's making it larger. It looks like we're making whatever voltage is here larger by 10. Okay, let's check that out one more time. Let's change this V in. Let's make it 2 volts. Let's see what happens. My guess is that this is going to be 20 volts, but let's see. Alright, 2 volts on the input now. Now, I'm going to run a little faster through this. All right. Rule number 1, no current in or out of any of our inputs. Cool. All right, that didn't really help us. Rule number 2, do we have a closed loop? Absolutely. So both of these should have the same value. If this is 2 volts, this must be 2 volts. If this is 2 volts, we have ground over here. Current's flowing from higher to lower. So now if we want to know the current, it's going to be 2 volts divided by 1,000. 2 milliamps. All right, did this 2 milliamps come from up here? No way, it had to have come from over here. All right, so now we can figure out our voltage drop. It's just going to be 2 milliamps times 9K. 18 volts over here. Oh, sorry. 18 volts across our 9K. And if we have 18 volts and this side is higher than this side by 18 volts, this side was 2 volts, this must be 20 volts. All right, so what did we make? Let's give this a name. It looks like it's amplifying. It's making the output bigger than the input. And it looks like it's not inverting it, right? Our input's positive, our output's positive. So having little imagination, let's just call this the non-inverting amplifier. And if we want to know the equation that uses these feedback resistors, V out is equal to RF divided by R1 times V in. Plus 1. So our gain is dictated by the ratio of these two resistances. 9K divided by 1K gives us 9, plus 1 gave us 10. V in times 10 gives us a V out of 10 volts. Same thing is true over here. 9K divided by 1K gives us 9. 9 plus 1 gives us a gain of 10. 10 times our input of 2 volts gives us an output of 20 volts. Okay, so to know what an op-amp is doing when we have voltages and values for this, we don't need to memorize any equations. But the equation for this very common circuit is given by V out is equal to RF divided by 1 plus 1. So that's a non-inverting amplifier. And I'll go ahead and leave this lecture as this. Okay? So we really covered three very useful and crucial circuits when beginning with op-amps. We covered the comparator, we covered the voltage follower, and we covered a non-inverting amplifier. Those are the fundamental tools that we need when we're starting to interface analog circuitry to digital circuitry. Okay? So I'll go ahead and leave this off there. Thanks.